Okay, hi everyone. Welcome to the second day of OPODIS. For today's keynote, we are really happy to have Jukka Suomela from Aalto University. And Jukka did all of his degrees at Helsinki University, which is cool, and now has a large and very prolific research group at Aalto. Jukka has won several Best Paper awards, including last year's Best Paper at Fox. And Yuka does really deep and fundamental and perspective-changing work on the local model of distributed computation. And some of this he's going to tell us about now. So Yuka?
Many thanks. So thanks for inviting me here, and many thanks for everybody who is here. I'm very happy to talk about this specific topic here at OPODIS, because OPODIS is bringing together people who are interested in theory and also people who actually care about what we can do in practice with computers. And just a couple of practical things. It would be really, really great if as many of you as possible could switch on your video cameras. It helps a lot if I can see something else besides black boxes here on my screen. So I'm getting at least a little bit of feeling that somebody is actually following or understanding what I'm saying. And I'll be happy to take questions also during this talk. So you can post questions on Zoom chat, or you can use Zulip. Both are fine. I'll try to follow these, and I'll be very happy to answer questions also during this talk. But let's actually get to the business. So what I want to talk about is the foundational question of computer science. What we really want to know is what can be automated? Where can we basically replace human thinking with some computer algorithms? And now the question I'd like to see all of us think about today is, can we actually automate our own work? And by our own work, I will be focusing here on theoretical aspects of distributed computing. I'm a theory person myself, so I'd like to see all of us think about how much we can automate our own work in understanding theory of distributed computing. So let's think about typical theory papers in OPODIS, or let's say typical papers in theory conferences like PODSI and DISC. And let's stop to think about how much of the work is usually done with computers. And I'm not referring to something like people are using computers to typeset their papers in LaTeX or something like this. I'm actually referring to this, let's say, intellectually challenging part of problem solving. And I think in many cases, the answer is relatively little. And I'd like to encourage all of us to think about how much of it could be done with the help of computers. So let's think about our usual process by which we are, let's say, producing research results. We start with a question. Of course, we're asking many different kinds of questions, but let's say a relatively stereotypical research question in theory of distributed computing is something like this. We fix some task X. We have in mind some model of computing M. And then we'd like to know, is there an efficient distributed algorithm for solving this task in this model of computing? Okay, and how do we answer these questions? Well, I think usually the most common approach is that we just bring together a bunch of smart people, and then we spend a lot of time thinking about these problems, spend a lot of time drawing figures on whiteboard, and then eventually, after a lot of manual work, the end result is something like we have an algorithm, we have algorithm analysis, we have proof of correctness, or if we realize that this cannot be done, then we have a lower bound proof and things like this. Okay, so what I'd like to ask is, can we replace this middle component here, where we have a bunch of smart people? Can we replace it with a computer? And could we imagine something where you can just take a computer program, enter the description of the problem and the model of computing you are interested in, and then decide, okay, do I want to get automatically today a lower bound proof or an upper bound proof? And then click a button, and then here you got a nice new theory result. Now, I guess at this point, some fraction of you are already probably wondering if I have lost all of the remaining sanity that I may have had, because like at first it feels like something like algorithm design or proving a lower bound or something like this. This is an example of the kind of activity that definitely needs human intelligence. And if you think about like what is the state of the art in the present day, let's say artificial intelligence, okay, computers are maybe able to tell if a picture is showing a cat or a dog, but how can we even imagine that computers would be able to do our work? After all, we are supposed to be doing something slightly more advanced than telling if something is a cat or not. So I'd like to start by giving a walkthrough of a toy example that shows that actually there are settings in which everything like algorithm design and lower bound proofs, it can be fully automated. I'm emphasizing that this is, let's say, a maximally simplified toy example. So if in the coming slides, if you're wondering like, okay, why am I making all of these strange assumptions? I'm just trying to keep this as simple and concrete as possible. And I think these examples may be familiar to some of you, but still I'd like to spend some time convincing all of you that there are at least some settings where everything that we are doing actually can be automated. And let's look at more challenging questions after this simple example. So the setting that we're going to study now is computer networks where our network is a cycle that consists of n computers. And as I said, we are going to simplify things a lot. So I'll be assuming that we got a globally consistent orientation. So basically, we have a graph that is directed and all nodes have out degree 1 and in degree 1. And the model of computing that we are using is the usual local model of distributed computing. This is a very strong model. We don't limit anything like message sizes, local computation. We assume that all nodes are already labeled with unique identifiers, so we have symmetry broken and things like this. And the only thing that we care about is the number of synchronous communication rounds until all nodes stop and announce their own part of the solution. And what are the problems that we are studying? Let's look at any problem that you can define, any discrete problem that you can define in terms of local constraints. So we have a setting where we have some finite number of output labels. Maybe these output labels are, for instance, 0 and 1, indicating which of the nodes have been selected. Or they may be, let's say, small numbers that are representing some kind of coloring or whatnot. And the key assumption here is that we are looking at problems that can be defined in terms of some local constraints. Basically, we have a relation that tells which local label sequences are valid. Let's look at an example. Let's look at something like, let's say, a maximal independence set. A set of nodes where no pair of adjacent nodes are simultaneously selected, and we'd like to have something that is maximal in the sense that you cannot add any additional nodes. And if I give you some candidate solution. It's actually enough that you look at a sliding window of size 3 and you check all triples of nodes. And if you see any triple that indicates that this cannot be a maximal independent set, like for instance here, in a maximal independent set in a cycle, you cannot have 3 consecutive zeros because you could add the middle node to your independent set without violating independence. So if you see a triple that is bad, we know that this is not a valid solution. And conversely, if all triples are good, we know that this is a good solution. So maximal independent set is an example of a problem that you can represent in terms of these local constraints. And there are many other problems that you can imagine that you can represent using local constraints. And I've just selected here 5 examples that are enough to illustrate the point that I'm making. So there are problems like 2 coloring, 3 coloring, independent sets, maximal independent sets, and then just to pick a really random example, distance 2 coloring with 3 colors, not because it's an important problem, but because this is demonstrating that I can just come up with silly problems that nobody has ever studied before and plug it in to this framework and see what happens. And here, if you think about these problems, for instance, something like 3 coloring, you can specify 3 coloring by listing all pairs of labels that you can see in a cycle. While something like maximal independent set, you need to have at least a window of size 3 to have a specification of this problem, but window of size 3 is enough. So any problem that you can specify by listing what are valid configurations within some constant size window is a good problem from our perspective. All clear so far. You can send quick questions in Zoom chat if anything is unclear. I just want all of us to be on the same page here. Now, okay, we have a problem that is of this form. And as you can see, this is an infinite family of problems. You can easily come up with new problems of this flavor. And now what I'm claiming is that if you have this kind of a problem in this setting, then you can do algorithm design and lower bound proofs in a fully automatic manner, in the sense that I can write down the problem specification like this, problem X. And then I can feed this problem specification to a computer and out comes an answer like, okay, this problem has in the local model complexity that is theta of log star of n, and here is an asymptotically optimal algorithm for solving it in log star of n time. And when I say efficiently, in this case, I mean that the running time of this algorithm, this centralized algorithm that is figuring out what is the most, what is the best distributed algorithm is going to be something like polynomial in the size of the problem description, in the size of, for instance, the list of feasible configurations. And how do we do this? I'll use this maximal independent set problem as an example of how do we approach these kinds of questions automatically with computers. So let's just write down all of these configurations that we may see in this problem. And let's consider each possible configuration and see what are other configurations that are compatible with it. Compatible in the sense that if you have a node that is in the middle of this orange configuration, then its successor might be in the middle of one of these blue configurations. You're basically just shifting these configurations by one and seeing that these overlapping parts agree. This is, of course, something that you can do in a mechanical way in polynomial time in the size of this list. Just basically check all pairs. And then we construct a graph where, for instance, if this orange configuration is compatible in this sense with these two blue configurations, we add links, we add edges, directed edges from orange to blue. And this way we construct a directed graph where nodes are configurations and these edges indicate which configurations are compatible with each other. And this way we get a graph, and it turns out that looking at this graph is basically all that we are going to need. So we can take all of our problems that I mentioned here, 2 coloring, 3 coloring, independent set, maximal independent set, distance 2 coloring with 3 colors. And if you think about this, you will get these kinds of graphs. Okay, so now what can we do with these graphs? Let's look at the first example here, this independent set problem. What we can observe here is that this happens to be a graph where we have a self loop. And of course, checking if there is a self loop in a graph is a very simple mechanical task. And it turns out that if there is a self loop, it's easy to see that the problem is solvable in constant time. Actually, it's solvable in this setting in 0 rounds, basically because a self loop indicates that a constant output is fine. Well, this is not a big surprise, of course. An empty set is an independent set, and finding an empty set is pretty easy. But the key point here is the following. A problem in this of this form is solvable in constant time if and only if there is a self loop in this graph. And why is this the case? Well, if there's no self loop, then if you imagine any solution and see how this solution is implying a walk in this graph, then you see that when you move from a node to another node, you're always changing configurations, which means that you're always everywhere locally breaking symmetry, which is already enough information so that you can solve problems like 3 coloring in constant time once you have this symmetry breaking information. And we know that 3 coloring cannot be solved in sub-Lookstar time. So no self loops immediately implies that problems have complexity at least Lookstar of n. So by checking if there are self loops, we immediately know if the problem is constant time solvable or not. And we also know that the next possibility is Lookstar. Okay, this case handled. Let's look at these other cases where we don't have self loops. For instance, here we have this maximal independent set problem, which is no longer trivial because, for instance, empty solutions are not good. And let's now look at this graph. And let's look at, for instance, this orange node. Let's try to think about walks that start and end in this orange node. One possible walk takes 1, 2, 3, 4, 5 steps. So we know that there is a walk of length exactly 5 that starts and ends in this orange node. Another possible walk again starts here. We take 1, 2, 3, 4, 5, 6 steps. In the previous example, we had a self-returning walk of length 5. Now we have a self-returning walk of length 6. I guess you start to see the pattern. I can also construct a self-returning walk of length 7. And if we generalize this, we can see that this orange node, this orange configuration happens to have a property that they are self-returning walks of length k whenever k is at least 5. Okay, what's the point of all of this? Let's introduce a definition. We say that a configuration is flexible if this property holds that they are self-returning walks of any length, at least k0, where k0 is an arbitrary value. So this is the definition. And now, by the way, I'm not going to prove this, but it's maybe not immediately obvious that you can detect flexibility in polynomial time. If you are, let's say, lecturing some, let's say, graph algorithms course, this might be a nice exercise for students to figure out a polynomial time algorithm for detecting which nodes in a graph are flexible in this sense. But believe me, it's really something that you can do in polynomial time. So flexibility is something that is polynomial time detectable. Okay, why do we care about flexibility? Well, as soon as you have something that is flexible, you know that the problem is solvable in log-star time in the local model. And actually, here it doesn't matter whether we are looking at randomized or deterministic local model, the same thing. And the algorithm is very simple. If you have a flexible state where this flexibility parameter is some value k0, let's say 5, then we are going to first use log-star time to split our cycle in segments of length at least 5. Let's say segments of length between 5 and 100 is fine, as long as we have some constant upper bound and this lower bound that is k0. This is fine. This is easy to do in log-star time. One way of doing it in log-star time is, for instance, finding a maximal independent set in log-star time and then finding a maximal independent set among those independent nodes and repeating it until you have, let's say, long enough gaps between two nodes that you have selected. And then we just blindly put this orange configuration at all boundaries of these segments. And that's it. Then we have constant length gaps, and by flexibility, we know that we can fill in those gaps. So the whole running time of this algorithm is just log-star plus constant, so log-star. So flexible implies that a problem is solvable in log-star time. And this is also a complete characterization of problems that are solvable in log-star time in this setting. Because if you have something that is not flexible, if you don't have anything that is flexible, meaning all configurations are non-flexible, and you consider any solution that you construct for your large cycle using these non-flexible configurations, then it means that, of course, you must be using the same configuration, because there are only finite many of those, the same configuration twice in locations that are very far from each other. And because we didn't have flexibility, if we are using the same configuration twice, we need to know that the distance between these two configurations is correct. Like the distance has to be, for instance, 0 modulo 2 or something like this. This is always what happens when you don't have flexibility. And then it means that you basically need global coordination to solve any problem where you don't have anything that is flexible. So we immediately get a lower bound that is linear. So problems are solvable in log-star time if and only if there is something flexible. And you can even extract an optimal algorithm for solving this problem in log-star time as soon as you know what is flexible and what is this flexibility parameter. And this basically means that now we are done. You take any of these problems, you check if they are self-loops, constant time solvable, trivial algorithm. If not, you check what is flexible. And it turns out that, for instance, among these examples that I have here, these two problems happen to be flexible. If you check, actually all of these states are flexible in these two problems. And For those problems that are flexible and don't have self-loops, we know that they are solvable in log start time. Their complexity is also log star. There is a matching upper and lower bound. We can construct in a mechanical way an optimal algorithm for solving these problems. And everything else is going to be inherently global. So all of these other problems that don't have anything flexible require linear time, even to check if this cycle happens to be a solvable instance. So basically, this is exactly what I promised. We can take the description of any problem in this formalism and feed it to a simple algorithm that checks for self-loops, checks for flexibility, and out comes information about the complexity of this problem and what is an optimal algorithm for solving this. So now, usually what people think at this point is that, okay, first it sounded like I'm talking about something that is like complete science fiction. And now it seems that, okay, well, this is boring. This is trivial in this case. Like we didn't even need to use any thinking. We were just constructing a graph and looking at simple graph theoretic properties of this graph. Like I mean, where's the big? The point really is that I hope that this toy example illustrates that at least in some cases, this whole idea of fully automating algorithm design for algorithm design and lower bound proof construction is something that can be automated. And moreover, it can be automated in a very simple way. And now, if you start to think about this, there is some setting where this automation is completely trivial. Now, what happens once we start to step slightly outside this trivial region? We start to encounter settings where algorithm design is not really trivial, but it still can be automated, at least in some cases. And now, I think a key question here at this point is, what are these other cases in which algorithm design and lower bound proofs actually can be automated? By the way, any questions, comments, observations, objections at this point from anybody? If not, let's continue. So in this toy example, I was talking about directed cycles. You can do similar things with undirected cycles. You can do similar things with paths. But let's now step outside this toy example and let's look at something that is somehow fundamentally different from the case of cycles and paths. Let's look at networks that are, let's say, two-dimensional grids. And let's now try to understand on a higher level what is actually going on here. If you look at, for instance, these local problems, local checkable problems, in cycles and paths, basically a solution can be seen as representing the execution history of a finite automaton. While on grids, you can actually engineer problems where solutions necessarily have to encode something like the execution history of a Turing machine. Now, if you think about it, if you write down on grid paper the full execution history of a Turing machine, the contents of the tape, where is the position of the head, and so on, this piece of paper is actually locally checkable in the sense that if you make a mistake in writing down this execution history of a Turing machine, you can find it in some place. And conversely, this basically means that by constructing locally checkable problems, we can construct problems that are, let's say, at least as hard as please write down the execution history of a Turing machine. And then you start to see that, for instance, questions like, is this solvable in constant time, are all of a sudden related to questions like, is this Turing machine going to halt? Or does this execution history continue all the way to the other extreme of the grid? So we have this dichotomy here in the sense that in cycles and paths, we are studying finite automata, and many questions are decidable, and furthermore, many questions are actually efficiently decidable. While as soon as you have something like a grid, you immediately start to get problems that are undecidable, which at first sounds like very bad news for us. But let's keep in mind that undecidable doesn't mean that these are hopeless. It may be undecidable in general, but we may be lucky. So let's see what we can do even in these cases of, let's say, problems in grids and grid-like graphs. So one observation that we can make is that if we imagine there is some algorithm A that is solving a locally checkable problem X fast, let's say fast is here log star of n, then in general, an algorithm that is working in log star of n rounds, it can be a very complicated entity. Like, how do you even represent something like an algorithm that has a running time of log star of n in general as a, let's say, as a string in a computer? Yes, you can write it down as a Python program or something like this, but then any analysis of such a program is immediately going to encounter challenges related to things like, let's say, the halting problem. But we can normalize any algorithm so that any such algorithm can be written as a composition of two algorithms. First, you have an algorithm that finds distance k coloring for some parameter, some constant parameter k, and nothing else. And then you have the second component that depends on the problem x. And this second component just takes this distance k coloring and turns it into a solution for the problem that we are interested in. So there is always going to be, I mean, if there is any fast algorithm for solving this problem x, there is always also going to be an algorithm in this normal form. We just first use log star time to do this distance k coloring. And then you just apply a finite function to this, these colored local neighborhoods. Now, at first, this may sound like, let's say, a deep result, but it's actually not difficult to realize that this has to be the case, because basically this distance k coloring can be seen as providing us with locally unique identifiers. These colors are kind of identifiers that are unique at least up to distance k. And now we could just take an algorithm that is working in the local model, and we can apply it so that we are giving it these color classes that are providing us with locally unique identifiers. And if the running time is small enough, the algorithm doesn't say that anything is wrong here. Or conversely, if this algorithm fails with these locally unique identifiers, then it's also going to fail with some real choice of identifiers that just happens to look like this specific choice in this specific local neighborhood. So we can always normalize any algorithm. Okay, now you may start to wonder, like, how is this normal form related to anything that I'm talking about here? But the point is that now, if you want to do algorithm synthesis, if you want to try to use computers to find a fast algorithm for this problem X, We don't even know if fast algorithm exists, but let's be optimistic. Let's guess that there is a fast algorithm for this problem. Then we know that there is also a fast algorithm of this specific form where we first find distance k coloring. We already know how to do this, and then we just apply some mapping to these local colored neighborhoods. So we can simply do this. We start with case 1. And now, once we fix case 1, then this function b becomes a finite thing. And there are only finitely many possible candidates for this mapping b. We just check all of this. If any of this is good, we're done. We found a fast algorithm. Otherwise, we proceed case 2, case 3, until we find a fast algorithm or we lose interest in this problem. So basically, also in this much more general case, I didn't say anything about cycles or even anything about grids here. This works in general boundary grid graphs for any local problem. You have this basically a universal recipe for constructing fast algorithms if they exist. Of course, I started by saying that this whole thing is undecidable. So where is this undecidability hiding here? You might first think that, okay, this part of checking if a candidate is good, this has to be something like the holding problem. But this is actually not a problem. Once you fix a value of k and a candidate mapping b, it turns out that this problem, this question of checking if this candidate is really solving problem X is a finite amount of work, maybe a large amount of work, but it is still checking finite number of cases. And then this real undecidability comes in this part. I said that some k exists. It's a constant k. Some constant k has to exist if the problem is solvable fast. If and only if the problem is solvable in, let's say, log start time. Then a constant k has to exist. But if you start looking for such a k, you check case 1, case 2, case 3, you don't find anything. You never know when to stop. Or let's say in the general case, you don't know if you have already checked all reasonable values or if you need to just search further. But in some sense, the good news and the bad news is that this is not really the obstacle here. The obstacle usually is that as soon as you reach values like case 3 or case 4, this amount of work that you need to do to check all possible candidate functions gets astronomical, because usually these things are something like doubly exponential in k in terms of, let's say, at least a naive amount of effort that you need to go through. They are, let's say, exponential in k many possible colored local neighborhoods, and then an algorithm is then something that is exponential. I mean, the number of different algorithms is something that is exponential in the number of colored neighborhoods. So this sounds like, okay, nice things in theory, but it doesn't give us anything in practice. But this is actually the wrong intuition here. It turns out that exactly this thing, or let's say a refined version of this thing, is sometimes doable. First of all, we can, of course, engineer problems where the smallest k that makes it solvable is something like, whatever, 1,000. I can engineer such problems. But if you pick a problem that is somehow, let's say, natural, something that we might want to actually understand and study, it turns out that in many cases, relatively small values of k, like case 1, case 3, is already enough. So this is like one piece of good news. And the second piece of good news is that there are many ways in which we can make this approach more practical. For instance, when we are looking at something like two-dimensional grids instead of general graphs, we can replace this distance k coloring with something like distance k ruling sets. Once we do this, even though everything still is like doubly exponential, if you check the constants, they are much more reasonable because the number of possible ruling sets locally is not so astronomical in if you consider small local neighborhoods, while the number of possible colorings tends to be something really horrible, simply because the number of colors that we need has to be horrible. So this is one thing that we can do to make it practical, or let's say more practical. And another thing is that, of course, we don't need to go through all candidates for this mapping B. We can just represent this question: is this candidate a good algorithm for solving this problem as something like, let's say, a CNF formula, and then we can use such solvers to check if good candidates exist or not. So in practice, this kind of a combination is something that is effective. So that, for instance, if you consider a natural problem, like you have a two-dimensional grid, you would like to find a 4 coloring of this two-dimensional grid. Not 5 coloring. 5 coloring is easy because 5 coloring is delta plus 1 coloring. You can find 5 colorings greedily. Finding 4 colorings is, let's say, more interesting. We seriously tried it with human beings. Like, we had a group of smart people sitting in front of whiteboard and spending a good amount of time, and we were getting nowhere. So this is a problem where actually computers were first to come up with an algorithm that is solving this problem actually in log start time. I now know, like with perfect hindsight, now I know how human beings should have approached this and so on. And now I could give a very simple and neat algorithm for doing this that is easy to explain. But the bottom line is that this actual first observation that this is doable in log start time using a relatively compact and concise algorithm. This first came from computers. So what I wanted to say here is that, okay, cycles and paths, it's almost like trivial. The case of something like grids, it's already way more challenging in the sense that we are already reaching some questions that are undecidable. But I wanted to show that also there is sometimes hope, because problems being undecidable doesn't mean that if you start with a natural problem of interest, you are immediately out of luck. Now, okay, cycles and paths, grids, like there are tons of other things out there. Of course, this bad news regarding grids, they basically apply to any graph family that contains large grids, or any graph family that contains, let's say, large grids as subgraphs or anything like this. But still, okay, we have, on the one hand, cycles and paths. Very easy. I was able to give basically a complete algorithm for handling this. And then we have bad news for anything that contains large grids. So what do we have here in between? Any suggestions from anybody in the audience? You can, for instance, type in the Zoom chat or Zulip or anywhere. So what, is this all that there is, or should we be looking at some interesting graph families that are somewhere here in between? Yes, good. Sparse graphs. Well, I think one challenge with sparse graphs is that grids are also sparse if we define sparsity in terms of, like, let's say, fraction of edges to nodes. So it seems that this bad news regarding grids are already bringing some bad news regarding sparse graphs. And by the way, they are also bringing bad news regarding things like planar graphs because grids are planar. But okay, fate, trees, yes. So trees are definitely something that does not contain large grids. And trees are definitely something that is, let's say, a bit more interesting than the case of cycles and paths from the perspective of distributed computing. And also, in addition to trees, we could also try to generalize it a bit, like let's say, having a look at graphs with bounded treewage, let's say constant treewage, or having a look at something like, let's say, Hilbert graphs that are at least locally tree-like. So I think all of these are examples of graph families that are excluding at least these pathological counterexamples that we have for grids. And if you look at these kinds of graph families, there are tons of open questions. We really don't know that much about these graph families. But the good news is that there are basically no known obstacles. We don't have a single undecidability result in these settings as far as I know. So it might be the case that in trees, bounded treewidth graphs, Hilbert graphs, all questions like this might be decidable. Maybe not efficiently decidable. We know that we already get something like p-space hardness very soon as you have, something like, let's say, labeled paths or whatnot. But at least it might be decidable. And actually, if you look at the simplest case of these, like trees, especially if you look at something like rooted trees or trees where you only care about internal parts of the tree and ignore leaf nodes or things like this, there are actually several positive results already known regarding these. I'm seeing here in the audience somebody nodding who is contributing on these kinds of results. So there are already some good news. So these good news are definitely not limited to something silly like directed cycles. So we do know at least a little bit about what goes on beyond this case of cycles and paths that is like fully understood. So, okay. So let's try to look at this slightly bigger picture. Like, I mean, I've been talking about some relatively specific examples, but let's see where all of this is taking us. And in some sense, what I'd say is that this line of reasoning is taking us towards kind of like meta computational questions. So if our traditional research questions are, okay, what is the best distributed algorithm for solving problem X? Now, if you move one meta level higher, we can start to ask questions like, can we design efficient meta algorithms that for some broad family of problems are able to find the best distributed algorithm for any problem from this family? And these kinds of meta questions are actually closely related to questions regarding classification of distributed complexity of problems. So by classification, I mean theorems of the form, if you take any problem from this family, it belongs to this class or this class or this class in terms of computational complexity. Something like we already know, we saw just that if you take any locally checkable problem in cycles, you know that it is either constant or log star or something global. There are way more interesting results similar to this, like if you look at locally checkable problems in general graphs, you know that it is in one of these four classes. And now, so this is one line of research that at first may seem like it has nothing to do with automation of our work, because this is a lot of manual work. But this is closely related to these meta-algorithmic questions, where we would actually like to show something like not just showing that any problem in this family belongs to one of these classes, but here is also an algorithm that is able to do this classification for any given problem. But if you think about these two lines of research, there are tons of connections between these, because first of all, many classification results are actually constructive enough in the sense that you can turn your classification lemmas and theorems into an algorithm that is doing classification for any given problem. And vice versa, if you have an algorithm that is doing classification for any given problem, usually the proof of correctness is also implying something like, okay, there are only these distinct classes of complexities available. So classification is one way of making progress towards the study of these metacomputational questions. And now, because we're talking about automating our own work, I'd like to emphasize that computers can also help with these classification tasks. And once you have solved classification, you often, as a byproduct, also get these meta-algorithms for doing classification. And why is this the case? Well, even if you are trying to classify some infinite families of problems, you can first focus on some finite subfamilies of problems and use computers to classify all of those. For instance, bounded alphabet size, bounded degree. Then this way you will identify interesting problems that remain unclassified, and then you can focus on those problems and learn something new about this whole problem family. Or if there are no problems left unclassified, then you got interesting conjectures that you can try to generalize, like, okay, all problems are of one of these types that we have seen with this finite family. Okay, now, how do we do this automation here? Because now it seems like I'm starting to talk about kind of like circular reasoning, like if the goal in doing classification is to be able to automate classification, so how do we do this automation here? But the good news is that there are general purpose techniques that we can at least try to use to automatically figure out the distributed complexity of any given problem from some broad family of problems. And the example that I just want to highlight here is the round definition technique, where you actually literally have an implementation where you have these two buttons. You can select whether you would like to prove today automatic lower bounds or automatic upper bounds. And of course, this is way too good to be true in general, and this really is the case. This is something that does not work with all problems. But nevertheless, it is something that is very often worth trying. So if you encounter an unknown problem, without much thinking, you can nowadays feed it. If the problem is of the right form, without much thinking, you can feed it to the round eliminator, and then surprisingly often, you'll learn something about the problem in a fully automatic manner. Not always, but often. And this is one of the examples of these techniques that are helping us to let's say, explore large problem families so that we can at least have conjectures that we can try to prove. Just an example of these success stories is this recent lower bound that we proved for maximal matching and maximal independent set. And if you look at the paper, it has got, I think, 6 co-authors, but it was not really just 6 people studying this problem in front of a whiteboard. It was 6 people plus 1 computer program that were studying this problem. And it was thanks to this collaboration that actually resulted in these results. Okay, I think it's time to conclude. So what I tried to talk about here is this question of, can we, those of us who work on the theory side of distributed computing, can we automate our work so that we would actually be using computers in practice to do at least some part of our research? And I tried to convince you that the answer can be yes. There are questions that can be solved fully automatically. There are known obstacles, but there are also tons of open questions related to these limits of automation. And the second point with which I'd like to conclude is that there are tons of opportunities for human-computer collaboration with many of these questions. And I think if you're a theory researcher who can actually write computer programs, really write computer programs in practice and use computers in practice to do something useful, then you're going to have a competitive edge because you can outsource at least a significant part of your work to computers. So with this, I'd like to conclude. So many thanks to everybody for listening. I'll be very happy to take questions and also comments and objections.
So we have a couple of minutes for questions, and then, of course, we can take any further discussion offline to Zulip.
So I don't know which one was first, but there was Isaac asking about this work relating to program synthesis. And yes, I mean, basically what I'm talking about here is algorithm synthesis. I mean, when we are proving upper bounds, when we're constructing algorithms, proving upper bounds, this is really algorithm synthesis. Yes, so in some papers related to this, we are actually using this terminology that it's algorithm synthesis. And this is something that makes especially people who are close to something like Boolean satisfiability very happy, because they usually want to think about these problems in terms of synthesis, program synthesis, and algorithm synthesis and circuit synthesis and so on. And so Faith is asking about this approach for asynchronous models, and I think you're thinking about asynchronous settings where there are some failures, because otherwise the answer is like sort of boring yes, because we can in this non-faulty setting we can basically just apply synchronizers and we are back. So this is a very good question. So we have used this kind of algorithm synthesis in isolation with some problems, like we would like to get, let's say, Byzantine fault tolerance and self-stabilization and things like this, and simultaneously reasoning about Byzantine fault tolerance and self-stabilization, even if you have a synchronous setting, is already for a human being kind of like annoying. And their computers are very good at, let's say, checking all possible scenarios, and then human beings that can try to extend it. But what I was talking about here today is, as far as I know, something that we cannot directly use in these asynchronous settings where we have failures. So I think this is a very good, like, it's not just a question, it's like very good, like, new line of research, like how to take these ideas or similar ideas and extend this so that they make sense for asynchronous settings with failures. So how are we doing with time? Should we move to the coffee break officially, or can Hagit ask?
So Jukka, first, thanks for a great talk. It was very educational and entertaining and really inspiring, actually. So regarding asynchronous computation with failures, so in some sense there is, I think you called it the meta-computation theorem, which is the asynchronous computability theory, the use of topology to study computability in asynchronous computing. And actually, there are examples where the best algorithms we know were not obtained by a computer, but in some sense in an almost automatic way. Like there's a kind of an algorithm that tells us what the algorithm should do. The downside, which I don't think is shared by your examples, the downside of this algorithm, I think specifically about the renaming algorithm for non-prime process numbers and number of processes, is that you get an algorithm that that has no intuition, that tells us nothing about why the problem is solvable. And I was, I don't know, intrigued or jealous of what you described for, I think was for coloring, that first an automatic solution was found by a computer, but then in a year or so you got somewhat an intuitive algorithm one can explain. And I guess the question is, what made it possible and whatever.
Yeah, I think in general this like question of when do we get something that we as human beings can interpret. This is it's a big challenge. And I think in some of these things that I mentioned, we get something that is like human understandable directly. But in some other cases, yes, we have this challenge that, okay, now we know that there exists an algorithm. We can write down this algorithm, we can look at it, and we understand nothing. And there, I think a couple of things that have helped us in various projects related to this have been the following. First is, the first one is that if you know that something is solvable, you know that you are actually looking for a nice algorithm instead of like usually actually be looking for a lower bound. Like just this, like having this one bit of information is helping you a lot to focus your like human reasoning. The second thing, one thing we have been doing is that we have, let's say, used computers to solve, let's say, the same problem for different parameter values. And let's say, for just to give a silly example, let's say that our parameter is degree. We solve the problem optimally for degree 2, degree 3, degree 4, up to degree 20, or something like this. We'd like to have now a human designed algorithm that is handling any degree, but we try to see what is the pattern here. What is this? What are these algorithms doing, like roughly speaking? Not caring about the details of any specific algorithm, but looking at these 20 algorithms and trying to detect some kind of patterns. Oh, now we see that it's roughly doing some kind of thresholding. So let's have the conjecture that we are doing thresholding, and then we ask computers what are optimal thresholding type algorithms, and now we have more information. Oh, it looks like threshold is going to be roughly half plus 1 over square root of delta. Okay, let's have this conjecture, and now we have something that we can try to prove by traditional means. So this kind of like computer-inspired algorithm design, where we get examples from a computer and human beings can at least find inspiration from these examples. This is something that worked in some cases, but I'm not promising that things like this are working in all cases. Then there was this question, let's see, lots of questions. By the way, I'll be happy to continue with these questions in also in Zulip. So if one of you can copy paste this like unanswered questions to Zulip, I'll be
definitely
happy to continue there, but I'll try to answer at least some of these.
So you should skip my question and go to the next question.
Yeah. So
offline.
Yeah. So Paolo is asking a very good question. Basically, in this toy example that we had, basically the only thing that we needed as human beings to do is identify what are like valid local sequences, and the rest was automatic. And I think this is a very good question. Like, what does it mean to specify a problem? Like, I mean, because if you're trying to ask computers, okay, please give me an optimal algorithm for solving problem X, what is the language we are using to specify this problem X that we are interested in? We must have some formalism for specifying this. And I think for many of these, let's say, locally checkable problems, we just start with this assumption that our language for specifying locally checkable problems is something like you list all feasible configurations, or you list all forbidden configurations, or something like this. But now this is a fair question, like, is this the right language? Or should our language be something like, let's say, I don't know, you specify logical formulas or something like this. And then you first turn these formulas into this list of configurations or something like this. I think this is like wide open, at least from our perspective. We just assume that when we say problem X, we mean something like this. And similarly, when we're talking about something like, let's say, optimization problems, we specify that, okay, these are feasible local configurations, and then we would like to maximize the number of ones subject to these local constraints or something like this. But still, this has been usually our language. I'd be very happy to hear, let's say, suggestions of how to do this properly. What would be the right language for something like this? Keren was asking about randomization, and I think, for instance, this toy example that I had, their randomization doesn't change anything. Like, you still get exactly the same algorithms, the same complexities, the same everything. Also in some cases, like grids, it turns out that randomization doesn't change anything. But of course, these are like, I'm cheating with these answers because I'm giving those answers where the answer is boring. It doesn't change anything. So I think more generally, randomness is interesting. We have once studied problems like, let's say, optimization problems with the help of randomness. Something like finding a large cut with the help of randomness. And there, the way in which we approached this was, we kind of thought that random bits are part of our input. And then we're finding, let's say, algorithms that are working basically well on average over all possible inputs, which means that if our input bits are really random bits, then this algorithm is working well, let's say, in expectation. But I think there are tons and tons of interesting questions out there related to how to really handle randomness, because these tricks usually result in something like you need to guess in advance how many random bits you're going to need in your algorithm, for instance, which is kind of like cheating. It's nice if a small number of bits is enough for a nice upper bound, but it doesn't tell much about lower bounds.
Isn't that always true, though, so that you can reduce the number of random bits and maybe introduce some small probability of error? It's true in many settings.
Yeah, it depends on the problem. I mean, and especially in many of these cases, we'd like to have in these computer experiments really small numbers of random bits, and like the difference between, let's say, 1 versus 2 random bits in your local neighborhood, this can make a huge difference. The difference between 100 and 101, this is let's say, easier to negotiate. But yeah, so I think, so the next session is starting in 3 minutes. So I guess I'll really need to stop talking here, and I'd like to thank everybody for excellent questions, and I'll be very happy to continue discussions in Zulip regarding all of this. So thanks, everybody.
Thank you so much, Jukka. Let's thank Jukka again.